All right, here we go, back in business. But actually not really, because I still have to find okay, I'm sorry. Here we are. Okay, so did you guys read about critical points? Okay. So first let's talk about this. You guys read about finding extreme values. So first of all, remember the first bullet point was what are absolute extreme values? And we learned about that. Then we talked about what are local extreme values or relative max, and extreme is just, so an extreme is a max or a min, right? And then you read about how to find extreme values. How can we find them? Well, the interior domain points, this is on page 1989. The interior domain points where the function has the local extreme values are points where either f prime is 0, like Robert suggested, or f prime does not exist. Okay, if a function has a local max or min value at an interior point c, if f prime of c exists at c, then f prime, what?
Wait,
oh.
Yep, exactly, miss.
If f prime doesn't exist, isn't that vertical?
Okay, so let's talk about this. This is what happens in math, and then you know what do you do when you're like, what? What do you do next?
I don't know. We're stuck at home by ourselves.
No, you have to no, don't go to YouTube yet. You could do that eventually. You reread it, and you reread it slowly, and you what's the word? You parse the sentence. Okay, that means you pick apart at it. You break it apart. You dissect it. So let's talk. If a function has a local min or max value at an interior point C of its domain. This is called a conditional statement, an if-then statement, right? Do you understand this part? Can you draw a picture? Does this make sense? If a function has a local max value, if a function has a local max or local min at an interior point C of its domain. Does that make sense so far? Can we all draw a picture of what that means? So, ooh. Right? So let's just say theorem 2. Okay, so it's saying if a function has a local max or min, let's go for a max at an interior point of its domain. So we have a graph. Okay, let's say the domain is all real numbers. There's going to be C in the interior point. So let's just put a random C. Okay, at C, we're saying what is there? A local max or min. So let's make it a max. So maybe something like this.
So just saying if a function has a point C that is a max or min in its domain.
Yes. See, he's breaking it down. Does that make sense so far?
Yeah.
Is that all that the sentence is saying? If a function f, oh, okay, so we got to call this f. Drawing pictures helps, has a local max value or local min at an interior point C of its domain. Okay, so here the domain, let's say, goes from A to B, okay? So let's say the domain is from A to B, but C is an interior point, ¿que no? Que sí. And if f prime exists at C, what does that mean? That means the derivative actually at C exists. The derivative here exists, right? What is it? Why does it need to say that? Because sometimes it could actually not exist, right?
Oh, when it's the half, when it's just an absolute.
Okay, so the f prime does not exist when what? What are some examples of when f prime does not exist? When the function is, what is it called? It's discontinuous. Thank you. Such as what? Wait, corners, cuts, jumps and holes, jumps and holes. Isn't that non-differentiable? Oh shoot. That's what we meant to say, you know? Because continuous just means that it's just not, you know, it's a smooth function, or you don't have to pick up your pencil. What we care, remember, what does it mean to be differentiable? To able to differentiate, able to have a derivative. So non-differentiable, such as corners, cusps, jumps, holes, vertical tangents, and vertical it's vertical asymptotes. So these are all the situations where the f prime does not exist.
Vertical tangent.
And vertical asymptotes. But this theorem is only saying if it actually does have a derivative. So it is differentiable. Then the only way it's going to be differentiable is what?
It's the derivative.
Then f prime of c must be 0, right?
So then at that point, the slope is 0.
Mm-hmm.
And that's how we know it's horizontal. The tangent is horizontal.
Mm-hmm. So basically they're saying if this is called an existence theorem, by the way, an existence theorem. There's a lot of theorems in math where there's a theorem basically that says something must exist or something must happen. So if there is a local max or min, right, at x equals c, and if f prime of c exists, then what? F prime of c must be 0. That's all we said. So there's a little mental gymnastics there.
So that's just what the theorem is.
Mm-hmm. That's all that said.
Wasn't that the same thing what Robert was saying yesterday? That
Is it the same thing that Robert was saying? It's definitely similar. Robert was, yeah. Didn't Robert say, hey, look, if it's a max, the derivative has to be 0?
yeah.
That's not exactly what he said. Because he said if there's a max, it has to be 0. But this book says, but also, Robert, f prime has to exist. Because maybe f prime doesn't exist, and it still might be a max or min.
So can we say
Is that just for local?
Local.
Can we say that B is the absolute minimum?
B is the absolute minimum. In this, yes. Well,
Yeah, basically.
Yeah.
for the-
mm-hmm. Okay, so let's go on. Because of theorem 2, are you guys okay so far?
Yeah.
Because of theorem 2, we usually need to look at only a few points to find a function's extrema. These consist of the interior points wherever f prime equals 0 or f prime does not exist. So basically, Robert found one piece of the puzzle. If f prime equals 0, there's probably a max or min there. Or there might be a max or min there. I can't say there might be a max or min there. Because Robert didn't say, remember how the reverse didn't work? Just because f prime equals 0 doesn't mean it's a max or min, but if it is a max or min, we thought f prime has to equal 0. But we forgot to mention yesterday that actually there's one other possibility. F prime might not exist, right?
For local?
Mm-hmm. Okay, so it says, and the domain, and so this is, that's why reading math and science, especially math textbooks, takes a lot of time, and that's why you need to take notes. Because even this sentence right here is packed with a lot of rules, a lot of legality. It's like case 1, this might be a possibility. Case 2, this might be a possibility. Are there any loopholes? Are there any counterexamples? You have to process it, think about it, really make charts and flow charts and stuff like that to really get to it. Because basically with math, there's nothing loose about math. There's no just that's the part of SCSC. No, there's no SCSC. It's sí or no, right?
You're talking really fast.
Okay, I'll try to slow down. Okay, I'll try to slow down. I guess my point is that when you're reading math like this, you have to take the time to really process it and then make a chart out of it to get all your information straight. Okay? Okay, so it says so basically if we want, the question we're trying to answer, you guys, is how can we find, by looking at an equation, how do we know where a function has local max or mins? Another name for this chapter is how can we find local maxes and local mins? Okay, we're not gonna, okay, that's one way if it's a parabola. Okay. So right now, so far we have some clues. Robert helped us yesterday. When we find local maxes or mins, one thing we could look for is wherever the derivative equals 0. Right? What's another place we might need to look for? Where the derivative does not exist. Because if we only worry about when it equals 0, we're going to miss the loopholes. But we also have to check what? The domain endpoints. Remember? We have to check the endpoints because that might actually be a local min as well. So at all other points in the domain, basically f prime is going to be positive or negative. So this is a very critical point. And it's called the definition of critical point. Okay, this is important. A point in the interior domain of a function f at which f prime is 0 or f does not exist is called a critical point. So this, we definitely have to write it down.
So in this drawing, it'd be C?
C is our critical point, that's right. So if you didn't write it down, please write it down. A critical point, basically. And we're going to call this the CP, okay? So we're going to use this abbreviation a lot. Okay? Critical point of a function is what? A critical point of a function is a point in the interior of the domain of f, a function, where what happens?
Where
F prime equals 0, oops. F prime of C equals 0, or f prime of C does not exist. Okay? Oh my goodness, I thought you guys were watching me. Okay? You guys need to memorize this and have this in your head for the rest of your life, but at least till the rest of this year, okay?
Year actually, 2014.
No. Until you take the AP test. And probably you'll remember for the rest of your life. That's kind of cool to think that I'm teaching you something that you'll carry with you for the rest of your life, even after I die. Okay, so at a critical point of a function is a point in the interior domain of a function where f prime equals c equals 0 or does not exist. Okay? Critical point. Does that mean there's a local max or min there for sure? No, but it's definitely critical enough that we need to check it out. Worth checking, that's right. Okay? All right. Should we draw a picture? What does it look like when f prime of c equals 0? So, like here, right? F prime of c equals 0. Or, like here, f prime of c equals 0, right? What about does not exist?
A jump.
Yeah, that's true, right? What if it's like this? Okay. At C, is the derivative going to be 0? No, the derivative is going to not exist. But isn't it kind of still a local max there?
Yeah.
Yeah, so it's worth checking out, you see?
At the very top, right?
Mm-hmm.
What's the very top of it?
Doesn't matter.
But yeah.
Oh,
Yeah, because like let's say like
okay.
f of c is like something and then like the other one
Mm-hmm.
is open.
Okay, then we'll talk about that. Let's draw one more. How about a vertical well,
Vertical tangent and vertical asymptote. Do they look different?
No,
Yes.
A vertical tangent is like it's continuous, but like it kind of just
vertical tangent looks like this, you know?
because
And so that's not a local max or min, but we have to still check it out. It's still a critical point. Okay? Okay.
But don't they have the same don't they have a derivative?
Yeah, I didn't draw it vertical enough, but
Wait, why is it non-differentiable?
because right there the derivative is going to be vertical, and vertical has no slope. Vertical line has no slope.
Okay. Oh yeah.
Okay, so in summary, okay, this is important. Did you guys find this to be important? Extreme values, that means maxes and mins, only occur at critical points or endpoints. Did you get that?
So does that mean each sum is a critical point?
Yes, because anytime the first derivative equals 0 is a critical point. And that's it. Not necessarily. That's very good. Not necessarily. It's critical enough that we need to test it out, but doesn't mean it is.
There's all these sequel P's with these.
Yes. Okay, so basically, this is something to note. So I'll call it a fact. What did they say? Extreme values. So those are maxes and mins, right? Only occur at critical points and endpoints. So basically, these need to be checked.
Wait, when it talks about extreme values, it means both the local and global, right?
Yeah. This does not
Oh my god, it's so shitty. What movie is it?
Les Mis.
Les Miserables.
Is it
Okay.
even, like educational?
The musical.
Yeah, it's a musical. It's about the French Revolution.
They're always watching movies. It's like they that's how they learn. Like
Okay.
That's what was that? That's misery after.
You guys should all read that. It's like 1,000,000 points,
which one?
and it's a really good book. Les Miserables by Victor Hugo.
How many pages?
It's really thick. It's like Roots thick. Maybe not as thick as Roots. It's a good book though.
You read it?
You guys probably saw in 9th grade. I read it, but I didn't finish it actually. But then I know the story because I saw the musical like 5 times, and like,
Great.
it was really hard to understand though for me as a 9th grader. Anyhow, so if you want to know where the extreme values are, what do we need to check? CPs and EPs, endpoints. Does it mean that every CP and EP is going to be a max or min?
No.
No, but still need to check it out. Got me? Okay. Okay, so then they gave us an example, right? Find the extreme values. Here, if we graph it first, it suggests that there's an absolute minimum of about 0.5 at x equals 0, and there seems to be a local max at x equals 2 and -2. However, f is not defined at these points, so there do not need to be appear to be maxima anywhere else. So basically, if what you said earlier, if f is not defined there, it cannot be a max. So if there's an open circle, to go back to your question, if there's an open circle, that doesn't qualify as a max or min.
Oh, it doesn't?
Okay. There doesn't seem to be a max anywhere else. How do we confirm this analytically? Do you guys see the difference? Here we just did it by looking at the graph. Visually we can see how many mins are there? Minimum right here. Local min right here at 0. How many?
Is that a straight line though?
It's actually not a straight line. Look at the equation. Could it be a straight line? No. It just looks like it. It's just like a very flat looking U. Okay? Now, there's a min here. What about maxes? It looks like there's one at 2 and -2, but actually it says it's not because there's an open circle there. F is not defined at those points.
So there's no max.
It's not an open circle actually. I think it's an asymptote. So there is no max. Okay? Now, but that's graphically. Most of the time you can't do it graphically. You have to do it algebraically or analytically. So here's what we're doing. The function is defined only for when this is positive, right? Because we have a square root. Can the square root be negative?
No.
Or can you have a negative under the square root? No. So 4 minus x squared has to be positive, so the domain is an open interval negative 2 to 2. Does that make sense? Yeah, so the domain has no endpoint, so the extreme values must occur only at, see, the EPs didn't work out for us. So the only other hope we have are the CPs, right? So what do we do to find the CPs? We rewrite the formula, okay? So this formula, we can rewrite it as this, so it's easier. We take the derivative. Once we take the derivative, what do we do to find the CPs? How do you find a CP? CP is when this doesn't exist or it's equals 0. So this doesn't exist when the bottom equals 0. But will the bottom ever equal 0? Yeah. And no, it won't actually, because the domain says that it has to be greater than 0, huh?
But can't you
I know, but look at, remember,
equal 2?
but remember, no, x can't equal 2 because it's not part of the domain, remember?
Oh.
Right? Because we just said 4 minus x squared has to be positive. It can't equal 0. So will the derivative never not exist?
No.
No,
So
in the domain. So the only CP is going to be
0.
0. And so we check out what happens at 0. The critical point is 0. And since it's a sole candidate, then, okay, now let's look. Okay, the only critical point is x equals 0. Okay, when x equals 0, the actual value output is 1/2. So 1/2 is the only candidate for an extreme value, it says. To determine whether it's an extreme value, though, you have to look at this graph. Okay, normally we would do something called a sign chart. Okay, as x moves away from 0 on either side, the denominator gets smaller, the values of f increases, and the graph rises. So basically, we know that when we go to the right of 0, this graph is going to be bigger than 1/2. To the left of 0, this graph is going to be bigger than 1/2. So that means x has to be the minimum, and the minimum, and it's the only minimum, and if you have the only minimum in an interval, then it has to not only be the local, but absolute. I said that really fast, I know, Robert. We know that this is the only minimum, locally minimum value, right? But if you are the lowest in your neighborhood, but there's only one neighborhood in the whole world, then you are the world's lowest, right? So we only have one local minimum, so it's also the absolute minimum, right? So the function has no maxima, local or absolute. It doesn't violate the extreme value theorem. Why? What did we learn about the extreme value theorem yesterday? Do you guys remember from your notes? Didn't the extreme value theorem say there always has to be an absolute max and min?
But that only says if it's closed.
On a closed, in a, say what, Robert?
If it is continuous on a closed, then max and min will be present.
Yeah, at max and min have to be present. But how come in this one the max doesn't exist?
It's open.
Because it was an open interval, and on open intervals, I can't guarantee anything on open intervals. Okay? And so that's why, right here, there's there is no I skipped example 4. Okay, so there is no, where am I? The function has no maximums, but that's okay because it's an open interval. To invoke, to call upon theorem 1's guarantee, there must be a closed interval. Okay? Now here are some examples. Okay? While a function a function's extrema can only occur where? Critical points or endpoints. Okay, let's look at here. Critical points and endpoints. And critical points exist where? When f prime of c equals 0 or f prime of c does not exist. So you kind of see the tree that kind of is forming in your head. If you want an extreme value, you have to have a CP or an EP, right? And the EPs are the left and the right, and the CPs are f prime of c equals 0 and f prime does not exist, right? So you see that little chart? little flow chart. You see how if you were going to be a computer programmer, you could program the computer to check for EVs by doing this. And then if yes, then this way. If no, then this way, you know?
Why does the computer need EVs?
Oh my god.
Well, we're going to learn, remember, in this unit about why this is,
Applying to real life.
yes, how it applies to real life. Okay, so while a function's extreme, it can only occur at critical points and endpoints. Not every critical point. Don't be fooled into thinking that every CP or every EP signals the presence of an extreme value. Look at this, right here. Is this a CP or an EP?
CP.
Okay, which one? What is a CP? X equals what? X equals 0 is a CP because the derivative equals 0. Is this a local max or min?
No.
No, why not? What is that called? That's a saddle point. It's called a saddle point. Doesn't it look like a saddle?
No.
That's a saddle point. We were just coasting there, okay? What about this? Is this a CP or an EP?
That's a CP.
Why is it a CP?
It's a vertical tangent.
And so therefore,
The saddle point.
the derivative does not exist, okay? The derivative, now is that a max or min? No, okay? All right, let's do this example together on paper. Okay, so hold on. Where's the first derivative test? The first derivative test didn't come out here? Huh,
Whoa, 4.2.
hold on.
Miss, we're not at 4.2 yet.
Woo, first derivative test comes out way later.
That's theorem 4.
Yeah, so we're going to just focus on okay, let's do it again, but you guys help me out. Find the absolute max and min of this function, okay, f of x equals x to the 2/3 power on this interval from -2 to -3. What kind of interval is this? Closed interval. So according to the extreme value theorem, what do we know about this closed interval? There has to be what?
An extreme value.
Extreme value, which kind of extreme values? Absolute max, and there has to be an absolute min because we close the neighborhood, so somebody has to be the tallest and somebody has to be the shortest. Okay? Now, it says find them. Okay, how are we going to find them? What are our choices? They're either going to be where? At the endpoints or at the critical points. So, okay, before we do that, let's just look at the graph. Graphically, what does it look like? Okay, so does it look like there's an absolute max somewhere?
No.
No?
At the end point.
Where? Which where?
On the right.
At x equals 3. Doesn't that look like the absolute max?
Yeah.
Okay, what about absolute min?
And 0.
At x equals 0, this looks like the min. Let's see if that will pan out analytically. Okay? Okay, so let's actually do this aquí. All right, so example 3 in book. Okay. F of x equals x to the 2/3. Did you know that x to the 2/3 looks like that? It's interesting, huh? Okay, so we know that we have to test endpoints and we have to test critical points, right? So how do we find a critical point?
Zeros and just 9.
To find CPs, find f prime of x, right? Yeah? So f prime of x is going to be 2/3 times x to the -1/3, yeah? Yeah? Okay, so that's going to be 2/3 times x to the 1/3, right? How can we find the CPs there? So can this ever equal 0?
The bottom is, yeah.
Can this f prime of c ever equal 0? No. Does that mean there's no CPs?
No.
What else could it be? It could not exist, right? So when x equals 0, f prime of 0 does not exist, right? Therefore, x equals 0 is a critical point.
I don't get it.
Okay, what don't you get?
How do you quickly
Because,
calculate?
oh, okay, so if for a function to equal 0, the numerator has to equal 0. Can 2 ever equal 0?
Oh, no.
No. For a function to not exist, the denominator has to equal 0. Can this ever equal 0? Yeah, when x equals 0. When x equals 0, this will be 2 over 0, which does not exist.
Oh.
So x equals 0 is their only CP. Okay? So if, yes.
Anytime x or the function does not exist, CP.
Whenever the derivative does not exist, the first derivative does not exist, it is a CP. Also, whenever the derivative equals 0, it's also a CP.
So whenever the denominator is 0 or whenever the numerator is 0.
Say that again?
So whenever.
Oh yes, the denominator or numerator equals 0 if it's a rational function. So let's think about it. CP, we have x equals 0. Endpoints, what do we have? X equals -2 and x equals 3, right? The question was to find the absolute, max, and min, right? So if there's a max and min, it has to either occur at 0, -2, or 3, right? Those are our only options. So what should we do to figure out which one's the max and which one's the min? Plug them into what? F or F prime? I want to know who has the biggest value and the smallest value. When I say value, do I mean value of F or a value of F prime? F. Right? So I'm going to plug in f of 0, f of -2, and f of 3. Okay? F of 0 is 2 over
No, it's 0. Because f is just x to the 2/3.
Oh, shoot. Thank you. I was like, what's going on here? Okay, so at f of 0, we have 0 to the 2/3, which is 0. 0 squared, and then third root. Okay, -2 to the 2/3 is, what is that? That means it's -2 squared, cubed rooted, right?
Yeah.
So it's going to be -2 squared is 4. Yeah, so it's cubed root of 4, or 4 to the 1/3. Okay. Which, okay, let's use our calculator. 4 to the 1/3 is, in the world? 1.587. Okay, f to the third power, f of 3 is 3 to the 2/3, which is 9, the cubed root of 9, which is 2.0800. Okay, so who's the biggest? 3. Who's the smallest? 0. So therefore, f of x has an absolute max of cubed root of 9 at x equals 3 and an absolute min of 0 at x equals 0.
Is this like in like the AP test would be like an FRQ?
Mm-hmm. Does that make sense, you guys? Questions on this?
On the AP exam for the FRQs, say you don't get like all the way to the end, do they still give you points for the work you've done?
Yeah, there's a rubric, and we'll look at FRQs and how they're graded. For example, this might be like, I mean, they actually wouldn't ask this specific problem. Like, maybe they'll ask this as part of something else.
Yeah.
This is too easy for an FRQ. But they might say, like, oh, they found these 3 critical points. So there's like 1 point for each, but then, like, the point would be for, like, the conclusion, like this sentence. So
Would that be, like,
being
part
able to
A?
write this sentence is very important. And then maybe 1 point for the derivative, something like that.
So it'd be like part A.
Yeah, it would be like 1 part. So let's just see if they did what we did. The first derivative, they found the first derivative, has no zeros, but it's undefined at x equals 0. So the critical point has 1 critical point and the endpoint. So they tested the critical point, they tested the endpoint. We can see from this list that the function's absolute maximum value is that, and occurs at this point. The absolute min is 0 and occurs. Wow! Couldn't have done it better. Cool. You guys feel good? Okay.
Son,
Yes.
can you explain why we plug in plug, yeah, for F?
Oh, thank you for asking that. Because basically that's a good question, Mario. Mario's question, you guys, is why do we have to plug it into F and not F prime? Plug the CPs and the EPs. Anybody know?
Like the position.
To get the position on the y-axis of the function. Because remember, we're looking for who is the absolute maximum of the function itself, of f. Right, Mario? We're looking for the highest y value of f. And obviously, basically what we said is the highest y value of f has to take place either here, here, or here. Right? Okay, here, here, or here. Now, if it happens here, we have to know how high does it go? How high does who go? The actual graph. The y on the actual graph. So we plug it in to see how high that value is.
Sorry.
Apparently this came out to be 2 something. How high is it here? Oh, it's 0. And how high is it here? It was like 1 point something. And so who is the tallest? The 2 is the tallest. It happened at 3. Who's the shortest? 0, and it happened at 0.
I see that.
Okay? How do we know that these are our only possibilities again?
Close.
Because it's a,
It's closed interval, so endpoints are a possibility, but how come we only chose it? How come we don't have to test all of these individual ones?
Because we saw the graph.
No, not because we saw the graph, but we determined that if there's going to be a maximum value, that's why that theorem is important. If there's going to be a local max or min, it has to be because there's a bump there and that there was like a derivative is 0. Or it had to be because the derivative didn't exist and so it cut off. There's no way that the derivative is not 0, it's like this, and this is going to be a max. Right? The max
Well,
only
what if
happens if it's the tallest of them all and there's a corner there, or it's like this, or it's like this and it stops. If it stops, the derivative doesn't exist. If it turned around, the derivative was 0. If it curved here, the derivative doesn't exist. See? And so that's how people found out that looking at derivatives is a really easy way to check how the graph behaves. Does that make sense?
Say like one more time.
Okay. This is holding? Okay. So think about it. If there's going to be a maximum, let me do it on paper so that Anna can see it too. If a graph's ever going to like have it be a maximum, a local maximum, it's either because it's going to go up and then go lower again, right? Or like this, you know, or maybe it goes like this and it stops, or like this and it stops, right? These are the only ways. Can you think of another, can you draw another way that you could actually be a maximum? That's the only way, right? And if this is the case, what happens here? The derivative is 0. What happens here? The derivative does not exist. What happens here? The derivative doesn't exist. Or it's 0. Yeah, it's hard to tell.
Depends if it's a closed.
Yeah. So basically, we figured out that the only way that you're really going to be the local maximum is because f prime equals 0 or f prime does not exist. That's what that theorem was all about. That those are your only options. And so if we know those are our only options, then basically when we look at a function, we only have to check these possibilities to see if it's going to be a local max or min. And I don't even have to look at the other parts of the graph. I only have to look for critical points and endpoints, and I will rest assured that all my extreme values have to occur there. So that's how people discover that, hey, if I want to know about the graph of a function, it's really convenient to look at the first derivative, and that will give me a lot of information about what the graph looks like. Does that make sense? So basically, we're kind of cheating. This is a technique, a trick, where we use our tricks to find the first derivative, and that can give us information, inside tips about what the graph of f looks like. F prime tells a lot of secrets about f.
What about like F double prime?
So f double prime will tell us a lot of secrets about
F
f prime, because f double prime is f prime's primo. Okay? I cracked myself up. I just made that up right now. Okay? All right. let's keep going. So okay. Now there are times when you're going to have to look at limits, and we're going to have to look at absolute values. And yeah, not now. I will leave you to, basically this is the same thing, but sometimes finding the derivative. Okay, you guys, on a piecewise function, how do I find the derivative? I have to do the derivative of the top and the derivative of the bottom. Okay, so that's one thing to gain from here. And absolute values. You guys should have already read these, and make sure you do read these, and let me know if you have specific questions, because these cases are important and they come up. But let's go ahead and look at your homework so that you guys don't feel completely confused or lost when you start your homework. So I could just give you guys some tips on your homework. We have 10 minutes.
We got 8 minutes.
We do?
Yeah.
It ends at 11:08?
11. It is not.
Oh, okay. Can I see this?
We're doing all homework.
You guys could do both, man.
No, we can't.
Okay.
No, we
Okay,
can't.
fine. Well, I'm
No,
being
we
too
can't.
easy on you.
No, you're not.
But I know you guys have college applications. Okay.
Thank you. Think
All right.
about this during Thanksgiving break too.
Okay, so Arlene just sticks it in there. Okay, so show all your work in your homework notebooks. Okay, you're gonna do this quick review. Okay, quick review. That quick review is gonna help you to just remember what you need to know about finding derivatives of functions. So that'll be good. And then basically, your job here is to identify the critical points and explain the reasoning why your value is a critical point. That's very important, okay? And then you're gonna do it on piecewise functions, okay? Which that means you need, oh, so this is a very short homework, very, very nice and easy. Okay, so you're gonna make sure before you do this, what example should you look at?
The homework. I mean, no.
No, example, see example
Wait, can you put on
5 in book. Before you do this, see example 5.
Oh, finding extreme values.
And don't forget this one. Okay? Alright, so let's look at number 1. Okay? It says, identify the CPs and explain. So y equals x cubed plus x squared minus x plus 5. Here we go. Oh wait, hold on. I like this. I like this. Okay. All right. So, okay, let's go fast. Okay, so what are we
doing?
We're doing example 1 from your homework packet. Okay, it's part B. So what is the first derivative? Well, first of all, how do we find CPs? What is a CP? Remind yourself, CP is when C equals 0 or f prime does not exist. So what do we have to do to find a CP? We have to find the derivative, right? So y prime equals 3x squared plus 2x minus 8, because now we're experts after chapter 3, right? And then we're going to probably want to do what? Factor, okay? And just for the sake of time, you guys all know how to factor. This is, when you factor, it looks like this, okay? So now what do we have to check? We have to check if it can equal, if y prime equals 0, right? Or we have to check if y prime is does not exist or undefined, right? So it's kind of nice to make a chart sometimes. Okay, you don't have to do this, but it might help you, especially at first. Well, how do we know if y prime equals 0? Let y prime, which equals 3x minus 4 times x plus 2 equals 0. What does that mean? X can either equal 4/3 or x can equal -2. Is this ever undefined? No. Okay? If it was a fraction, a rational, then we might have other times where it's undefined. What is this a test for? This is a test for what? CPs.
Wait, okay, so you know how x equals 4/3?
Uh-huh.
Maybe it was another way where it was like x equals 4/0, then it would be like does not exist, right?
Yeah, that would never happen
Okay.
in this side. Yeah.
Okay.
Yeah, but if it, yeah, then it'll be on the other
So
side.
we just found the critical point?
We found 2 critical points.
Oh, there can be
Okay? And so there can be no more critical points because no other situation will cause y prime to equal 0, and there's no situation that will cause y prime to not exist, right? So the only thing we had to do was identify CP. So your final answer, tell me your CPs and tell me why. Tell me why. Okay, so the first CP is x equals -2. Why? Because y prime of -2 equals 0. That's why. You have to explain. Okay, so you would say because, you know. And y equals 4/3 is a CP. Why? Because y prime of 4/3 equals 0. Okay?
So we just did number 1.
You just did number 1 on your homework. Do you guys see how this chart would help? But on this AP test, you wouldn't necessarily do a chart, but you would do a sentence. X equals -2 is a CP because y prime of -2 equals 0. X equals 4/3 is another CP because y prime of 4/3 equals 0. You see how that you could easily translate that into a sentence?
Yeah.
All right, guys.
So we just do 1?
So yeah, just do the first assignment, which includes the quick review and these 9 problems. Oh, I'm sorry. Does that make sense, you guys? Is everybody clear? Robbie, you clear about your homework?
Yeah.
Good.